In the last couple lectures, we've learned about the hydrogen atom, its orbitals, and electron spin. Now we're ready to discuss the remaining elements in the periodic table. So in this lecture, we're going to focus on the first three periods. Specifically, we'll talk about the orbital filling rules, including the Aufbau principle, the Pauli exclusion principle, and Hund's rule. And then with these, we'll look at the actual electron configurations for all the elements between hydrogen and argon. We'll also talk about how the trends we find in the electron configurations can be rationalized in terms of charge penetration and screening effects. The s, p, d, and f-type orbitals we learned about for hydrogen are also found in the other elements. But now we have more than one electron to put in those orbitals. So there are three general rules that offer guidance on how these electrons are filled in. First is the Aufbau principle. Aufbau is German for building up. The Aufbau principle is based on the idea that electrons prefer the lowest energy configuration. So when we place electrons in the orbitals, we start placing them in the lowest energy orbital, so the most stable orbitals, and we fill upwards. The second rule is the Pauli exclusion principle. We talked about this already in the last lecture. It states that no more than two electrons can be in the same orbital with the same spin at the same time. Because of this, we can have no more than two electrons per orbital, one with spin up and one with spin down. This ties into the Aufbau principle because it means we can't just put all our electrons in the most stable orbital. Rather, once we put two electrons in an orbital, it's full, and the next electrons have to go in a higher energy orbital. The third rule is Hund's rule. This rule is relevant when we have multiple orbitals with the same energy. Such orbitals are called degenerate orbitals. So when we have degenerate orbitals, Hund's rule says we should typically put one electron in each of the degenerate orbitals with the same spin before adding a second electron of the opposite spin to any of those degenerate orbitals. These will all become clear in a moment when we look at some examples. The other thing I want to mention before we do that, though, is these rules are general guidance, but as we see, there will sometimes be exceptions or subtle complications that make figuring out electron configurations a little more difficult than these rules might lead you to expect. But in general, these offer good guidance for filling up the periodic table. Here are some examples to help clarify these three rules. First, the Aufbau principle. It says we should fill the lowest energy orbitals first, or fill from the bottom up. So for example, if we had two electrons, the correct electron configuration is to put both of these in the 1s orbital, because this is the lower energy one. Putting one, for example, in the 1s orbital and another in the 2s orbital would result in a higher energy configuration for the electrons. And so this configuration on the left is the preferred one. This is the most stable because it has both electrons in the lower energy orbital. The second is the Pauli exclusion principle, in which we pair up electrons with opposite spin. So for example, if we have two electrons that are going in the 1s orbital, we have one spin up and one spin down. You can't have two electrons in the same orbital with the same spin, as would be the case in this example. If we have three electrons, well, we put our first two in here, one spin up, one spin down, and that has filled up the 1s orbital. And so then the third electron cannot go in here according to the Pauli exclusion principle, so then we have to rely on the Aufbau principle and start filling up the higher energy orbitals. And in contrast, something like this configuration on the right, where I have three electrons, two spin up and one spin down in the 1s, would be incorrect because it violates the Pauli exclusion principle. I have two electrons in the same orbital with the same spin. These first two both are in the 1s orbital with spin up, and that's against the Pauli exclusion principle. The third one is Hund's rule. For degenerate orbitals, you place one electron in each orbital with parallel spins before pairing any electrons. In this example, I have 6 electrons. My first two fill up the 1s orbital. Now that's full by the Pauli exclusion principle, so according to the Aufbau principle, I put the next two in the 2s orbital. Now it's full as well, and I have two more electrons to place in the 2p orbital. So I have many different ways I could imagine arranging these two electrons in the 2p orbitals, and Hund's rule says I should spread them out one electron per orbital before I start pairing any of them, and I should put them in the orbitals with parallel spins. The reason for this is that the interactions between same spin electrons turn out to be slightly more favorable than those between opposite spin ones, at least when they're in different orbitals. And so this difference is small, and it's much smaller than the energy difference between the 2s orbital and the 2p orbital, for example. So that's why in the Aufbau we fill up this orbital before adding A to the 2p. But once we have degenerate orbitals, and we have essentially many seemingly equivalent ways where we could arrange the electrons, the small energy preference for this sort of configuration wins out over one like this, for example. Now, to apply these rules to the elements, we need to know the relative energies of the orbitals. So in this lecture, we're focusing only on hydrogen through argon, or the first 3 periods. It turns out to do that, we need orbitals from the 1s up to the 3p orbital. This diagram here shows the relative energies of the orbitals in this set, the 1s, the 2s, 2p, 3s, and 3p, and that the energy generally increases as we move up this list. Now, this orbital energy diagram I'm showing here isn't to scale. These are just the qualitative energies, but it's enough for you to be able to figure out what the electron configurations are for all the elements in this section of the periodic table. The other thing I want to mention is that this orbital energy diagram here is completely consistent with the one I showed you earlier in the lecture on the hydrogen atom. So now let's go ahead and apply this to some of the atoms. Let's start with the first 6 elements, hydrogen through carbon. Hydrogen has just 1 electron. According to the Aufbau principle, we place that 1 electron in the 1s orbital, since that's the most stable configuration possible. It's the lowest energy orbital. It doesn't matter whether we draw the electrons being spin up or spin down. And as a shorthand, we refer to hydrogen as having a 1s1 configuration, with the 1s indicating the orbital and the superscript 1 here indicating how many electrons are in that orbital. Helium has 2 electrons. According to the Aufbau principle and Pauli exclusion principle, we place the second electron in the 1s orbital as well, but with the opposite spin to form an electron pair. We say helium has a 1s2 configuration, so there are 2 electrons in the 1s orbital. Now the 1s orbital is full, so when we go to lithium and have a third electron, the Aufbau principle tells us it should go in the next lowest energy orbital, which is the 2s orbital. Again, it doesn't really matter which spin we use for this 2s electron. The main point is that it's in a separate orbital from the 1s because Pauli exclusion says that this orbital is full, and the Aufbau principle tells us we have to put it in the next lowest energy orbital. So we say lithium has a 1s2, 2s1 configuration. Beryllium has 4 electrons, which is enough to completely fill the 1s and 2s orbitals, giving us a 1s2, 2s2 configuration. Boron adds a 5th electron. So we have 2 in the 1s, 2 in the 2s, and our 5th electron goes into the 2p orbitals. It doesn't matter which of the 3 2p orbitals we draw it in, doesn't matter what spin we give it, point is it just has to be in one of these orbitals. So boron has a 1s2, 2s2, 2p1 configuration. Now carbon. Carbon has 6 electrons. 2 in the 1s, 2 in the 2s, and the remaining 2 will go in the 2p. And according to Hund's rules, we want to spread these electrons out, 1 per orbital, before we start pairing any up. So these 2 electrons in carbon are going to go in an arrangement something like this, where I have 1 in this orbital, 1 in that orbital, and they both have parallel spins. It doesn't matter which of the 2p orbitals I put those 2 electrons in, as long as they are not in the same orbital, and as long as they have parallel spins. Let's complete the second period of the periodic table now, going up through the element neon. So to save space, we sometimes draw simplified representations of the orbital energy diagram, such as the ones shown here. When using these sorts of compact diagrams, it's your job to remember the relative energies of these orbitals. That 1s is the most stable, then 2s, then 2p. So we'll be filling electrons on these diagrams generally from left to right. The first 4 I show here are just repeating lithium through carbon that we talked about on the last slide. So let's continue with nitrogen. Nitrogen has 7 electrons. The first 2 go in the 1s, the next 2 go in the 2s, and we have 3 remaining for the 2p orbitals. According to Hund's rules, we place 1 electron in each of the 3 2p orbitals and give them all the same spin. So nitrogen has a 1s2, 2s2, 2p3 configuration. For oxygen, it's similar, but we have 4 electrons for the 2p shell. We'll start off filling the first 3 according to Hund's rules, 1 in the first orbital, 1 in the second orbital, 1 in the third orbital, but now we have a 4th electron and there's no other orbital we can put it in to give it the same spin. So now we have to start pairing electrons. So we put the 4th electron back here in this first one with the opposite spin. So oxygen has a 1s2, 2s2, 2p4 configuration in which we've spread out electrons across all of them, but because we have more than 3 and there are only 3 2p orbitals, we have to do an electron pairing. For fluorine, which has 9 electrons, we end up with 5 2p electrons, and therefore we're forced to pair electrons in 2 of the 2p orbitals and have only 1 of them left unpaired. So it has a 1s2, 2s2, 2p5 configuration. Finally, for neon, we have 10 electrons, which is enough to completely fill the 1s, completely fill the 2s, and completely fill all 3 2p electrons. And so it has a 1s2, 2s2, 2p6 configuration. Let's try a practice problem. Which of the following orbital configurations is correct for silicon, which has 14 electrons? Go ahead and pause the video, attempt the problem, and then resume when you're ready to hear the solution. Okay, so the energy of the orbitals here increase from left to right. 1s is the most stable, followed by 2s, then 2p's, then 3s, then the 3p's. So according to the Aufbau principle and Pauli exclusion principle, we're going to start filling from the bottom up and pair them up as we go. So I'll put 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 in the 2p orbital. That gets us up to 10 electrons. We'll put 2 more in the 3s orbital, which brings us to 12, and then we have 2 electrons left over to go into the 3p orbitals. According to Hund's rules, we want to spread those 2 electrons out across 2 different p orbitals, and we want to give them parallel spins. So the correct answer is C, and silicon has a 1s2, 2s2, 2p6, 3s2, 3p2 configuration. Now answer A is wrong because it violates Hund's rules. We paired up 2 electrons in the 3p orbitals before spreading out into the other ones. Now in answer B, we do spread the electrons out, but it still violates Hund's rule because we gave them opposite spins. Remember, Hund's rule says the 2 electrons should have the same spin. And finally, answer D is wrong because it violates the Aufbau principle. We should have filled the 3s orbital, which is lower in energy than the 3p one, before we started putting any into the 3p. The electron configurations in period 3, or the elements sodium through argon, are pretty much the same as those for period 2, except now we're filling the 3s and 3p orbitals instead of the 2s and 2p ones. For all these elements in the third period, the inner 1s, 2s, and 2p orbitals are completely full. As a shorthand, we often indicate this with this notation shown here, where we have neon indicated in square brackets, and that means we have a core of electrons involving a 1s2, 2s2, 2p6, which is the electron configuration of neon. Now, as we get further in the periodic table, we can also replace neon with whatever other element we want. For example, with argon, radon, etc. Or even early in the table, you could use helium to replace just the 1s2. So this is just a convenient way to represent electron configurations when we have a lot of electrons going around. Looking now at these configurations, you'll note that here I'm just showing the 3s and 3p orbitals because all of these have a neon core with the 1s, 2s, and 2p completely full. And so as you look at these, if you were to compare them to the configurations in period 2, you'd see that these are exactly the same, except instead of 2s and 2p, it's 3s and 3p. So for example, in sodium and magnesium, after filling up the neon orbitals, we have 1 or 2 additional electrons. Those go in the 3s as either 1 or 2 electrons. Once we get to aluminum with 13 electrons, we use 10 in the neon core, 2 in the 3s, and we have 1 left over that ends up in the 3p. Silicon, as we saw, ends up with 2 in the 3p orbitals spread out as shown here, according to Hund's rules. Phosphorus, like nitrogen, has 3 in the 3p orbitals, which gets spread out like this. Sulfur has 4, similar to oxygen, and we end up spreading out 3 of them, and then the 4th one has to pair up with one of these as shown here. Chlorine looks a lot like fluorine with 5 electrons in the outer p orbitals, so we end up having to pair up 2 sets of them and have just 1 unpaired. And finally in argon it looks a lot like neon, where we have the 3p subshell completely full. We've just seen that the elements in period 3 have electron configurations that are completely analogous to those in period 2. Lithium and sodium each have 1 electron in their outer s orbital, for example. Carbon and silicon each have 2 electrons in their outer p orbitals arranged in the same way. Nitrogen and phosphorus have 3 in the p orbitals, again arranged in the same way, and so on. As you move down a column of the periodic table, you expect that the electron configurations are generally going to be the same in the outermost orbital. The only difference is changing, for example, from a 2p to a 3p, but with the same electron arrangement in those orbitals. As we'll see later on in this unit, later on in this course, and even in future chemistry courses, the similarities in electron configurations lead to similarities in the properties and chemical reactivity of these elements. And this structure of the periodic table allows us to see these relationships easily and to rationalize a lot of interesting phenomena. As one example of this, consider the so-called noble gases, which are in group 18. This is the far right column of the periodic table. All of these noble gases have completely filled subshells. So for example, helium fills its s orbitals. The rest of these, neon, argon, krypton, xenon, and radon, all fill all the way up through their outermost p orbitals. So these completely full subshells, it turns out, are particularly stable, and they account for the very low chemical reactivity of these species, which is why we don't observe many compounds involving helium, neon, argon, etc. Finally, let's step back just a moment and ask, why is the 2s orbital lower in energy than the 2p orbital? Or similarly, the 3s orbital lower in energy than the 3p? There are 2 key concepts you need to understand: screening and penetration. So when the 1s orbital is full, those inner 1s electrons screen or block some of the nuclear charge from electrons in the outer valence shell. So for example, electrons in the 2s or 2p orbitals. Remember from earlier lectures that electrons in the n equals 2 shell will on average be further from the nucleus than those in the n equals 1 shell. So if we look at a lithium with a 1s2, 2s1 configuration, for example, the nucleus has a +3 charge. But the 2 negatively charged electrons in the 1s orbital effectively block or screen about 2 units of that nuclear charge from the 2s electron that lies further away from the nucleus. So in a sense, that 2s electron only feels an effective nuclear charge that's closer to something like +1 rather than the true +3 charge. If we now compare the 2s and 2p orbitals, we see from the radial probability distributions that the 2s orbital has a greater probability of finding the electron near the nucleus than does the 2p orbital because of this inner peak. And so in other words, we say that the 2s orbital penetrates closer to the nucleus than the 2p orbital does. What that means is an electron in the 2s orbital will experience a little bit less screening than does one in the 2p orbital. And that extra attraction to the nucleus because of the lower screening will stabilize that 2s electron a little more than those in the 2p orbitals, because those 2p orbital ones penetrate less and experience a greater screening from the inner electrons. So this is why the 2s electrons become lower in energy than the 2p, and similarly the 3s electrons lower than the 3p. Let's try a practice problem. Order the 3s, 3p, and 3d orbitals in order of increasing energy, that is, from the most stable to the least stable. Pause the video, attempt the problem, and resume when ready to hear the solution. The correct answer is B. The 3s orbital is the most stable, followed by the 3p orbital, followed by the 3d. We can rationalize this based on the penetration of these different orbitals as indicated from these radial probability distributions shown here. An electron in the 3s orbital penetrates the closest to the nucleus, and so it experiences the least screening from the electrons in the n equals 1 and 2 shells. An electron in the 3p orbital in red exhibits intermediate penetration, so it will be screened more than an electron in the 3s orbital, but less than one in the 3d orbital. The 3d orbital has the worst penetration and therefore experiences the most screening. And therefore, the electrons in the 3s are likely to be more stable than those in the 3p and then those in the 3d. So in conclusion, we've learned three key rules for filling electrons in the atomic orbitals. The Aufbau principle, which states that we fill electrons from the lowest energy orbitals up. The Pauli exclusion principle, which states that we can have no more than 2 electrons per orbital and that they must have opposite spins. And Hund's rules that tell us that when we have degenerate orbitals, we should spread out 1 electron per orbital with parallel spins before pairing any electrons. We also learned how orbital screening and penetration help determine the relative orbital stabilities that underlie some of these rules. Now these 3 rules work beautifully for the first 3 periods of the periodic table. In the next lecture, we'll talk about elements in later periods. As we'll see, the details start to get a little more complicated, and these simple rules of thumb don't always work perfectly. Nevertheless, the guidance these rules offer works for most of the elements in the periodic table.